looks like not everybody is here, but I'm going to start anyway. All right, so for those who are late, that means they're going to miss the news. Okay, so for today, I'm going to continue with the amplitude modulation. For amplitude modulation, let me see. Okay. Okay, can you see my screen?
Yes.
All right, so before I start, continue on the double sideband full carrier, let me do a bit of recap of what has brought us here. Okay, what has brought us to this point. Remember we started our amplitude modulation with double sideband suppressed carrier. Right, as far as AM is concerned, right, we started with double sideband suppressed carrier modulation, right? So in this double sideband suppressed carrier modulation, what we did is we just multiply our message with the carrier. All right, so that will give us the double sideband suppressed carrier signal, which is ST. Yeah, and well, generation is very easy. I just multiply them, then I produce that signal. And from here, when it reaches the receiver, how do I recover it? I recover it again by perform the same process. I multiply again with the same carrier that I use at the transmitter. And that will give me a product of these two will actually result in some baseband as well as components at the two times the carrier frequency. All right, so in order to recover, I need to pass my signal through a low pass filter, and that will give me my MT. That is for double sideband suppressed carrier signal. Okay, so for modulation, this is what I do, and for demodulation, this is what I do. Okay, so everything look very simple, very straightforward, and very nice. Problem is for double sideband suppressed carrier signal, right? At the recovery side or at the receiver side, we need to multiply with the carrier, which is synchronous with the carrier that we use at the transmitter. So in practice, basically, this is quite difficult to um, realize. Yeah. So this one require coherent detection or synchronous detection, right? Or synchronous detection. So if we are not able to synchronize these two carrier, then you see that our signal will be badly faded. Yeah. And so that is a problem with double sideband suppressed carrier signal. So we'll improve the situation a bit by introducing the double sideband full carrier. So in double sideband full carrier, what we did is, so in after multiply with the carrier, right, we add our carrier. We add the carrier to the signal. Okay, of course, these two are not exactly the same. That will give us the double sideband full carrier signal. So we send the carrier along, right? We send the carrier along with the modulated signal so that at the receiver, all right, at the receiver, this is your modulation side and this is the demodulation side. All right, at the receiver, we can actually recover using a rectifier or envelope detector, right? And that will be, then the same thing, what we do is we go through low pass filtering, and then we go through DC blocker, which is capacitor basically. All right, that will be for us to recover our MT. Okay, so that is what we have gone through so far. We have introduced the double sideband full carrier modulation technique. Okay, so now let's look at the double sideband full carrier techniques. It basically has two problems. Yeah, the first one is it actually wastes power. All right, it wastes power. Why waste power? We have seen previously that a lot of the power basically is being wasted in where is it? We're going to calculate later on, but you can see that a lot of power actually is used to send our carrier signal here. Huh? And then another problem is you actually waste bandwidth. Waste bandwidth meaning it actually in the both sideband, the upper and sideband and lower sidebands, they both of them carry the same amount, same information. All right. So for that matter, um, it's actually wasting bandwidth. It's using twice the bandwidth um, as actually what is not is actually required. Okay, let's deal with the first problem first. Yeah, waste power. So let's calculate the power. So the total power in the double sideband full carrier signal is the power in the lower sideband plus the power in the upper sideband plus the power that used to send the carrier signal along. Yeah, and then for double sideband suppressed carrier modulation scheme, the total power was used to send the lower sideband and the upper sideband only. We never send the carrier along. Okay, so let's do a bit of calculation. We want to actually see the efficiency or how much power is wasted. So now let's bring back our equation for double sideband full carrier, which is this one here. All right, so it consists of the lower sideband, which is this term, upper sideband here, and also the carrier. All right. So to get an expression for the total power required to transmit, I'm going to substitute. All right, do a bit of substitution because you can see later on that the power or the efficiency depend a lot on our modulation index. So using this equation, all right, and power in the lower sideband basically is this one. This is the peak amplitude. All right, peak amplitude of this lower sideband signal. So to find the power in the lower sideband signal, basically take the peak amplitude, divide by √2 and then square it. Right. So for any sinusoidal signal, the power is equal to the square of the RMS voltage. Okay. Of course, you have V square over R, V RMS square over 2 over R. But then in communication system, unless R is given, we always treat R as 1. Yeah. So in this case, my peak amplitude is Vm over 2 here for lower sideband and upper sideband. All right, V peak is Vm over 2. All right, so if I were to convert to Vm to MAVC, so that means this is MAVC over 2. All right, so my VRMS will be V peak over √2. So that will be MAVC over 2 √2. All right, so power will be VRMS square over R, right? V square over R. So in this case, we're going to use R equals to 1. Yeah, so that will be VRMS square. All right, so VRMS square for as far as upper sideband and lower sideband is concerned. All right, so that would be here half of MA square VC square over 4. All right, where does this 4 come from? this will come from the 2 square here, this 2 square, and then this root 2 after square will give you 2 here. Okay, then this is for lower sideband, upper sideband, same power, alright, because the amplitude for upper sideband and lower sideband are the same. And then the carrier amplitude is Vc, so it's just Vc square over 2. Alright, because the RMS value will be Vc over root 2. Vc over root 2 square will give you Vc square over 2. So this is a carrier power. Alright. So what we do next is we collect the common terms. So collect the common terms in these three expression here. So the common terms are Vc square over 2. Alright, so I have Vc square over 2. And then what I have left in the bracket will be 1. 1 is because I have extracted Vc square over 2 here. And then I have left is 1 plus ma square over 2. All right, you may want to go through the maths later on yourself. So that would be ma square over 2. Okay, next thing is what is Vc square over 2? All right, Vc square over 2, we know that is actually power in your carrier, which is this one here, Vc square over 2. All right, and therefore I substitute Vc square over 2 with Pc. So this is the expression for the total power in a double sideband full carrier signal. Yeah, and you can see from this equation, all right, the total power transmission that required to transmit the double sideband full carrier signal basically depends on your modulation index. All right, and also the power of the carrier that we use to transmit. Yeah, and you can see also from this equation, right, that the carrier component actually is going to occupy most of the power that we use. All right, whereas the sideband here, which is the ma square over 2, this is the total of the 2 sideband power, right, is actually quite small as compared to the carrier power. All right, depend on your modulation index. And remember from last lecture that the modulation index for double sideband full carrier can never be more than 1. All right, don't ever use a modulation index that is more than 1, because if you do that, your signal will be distorted, and then there is no way the receiver is able to recover it later on. Yeah. So as far as double sideband full carrier is concerned, the biggest value of your modulation index is 1. Right? So if you were to put the number 1 here to replace the ma square, so that means the power, all right, the proportion of the power carried by the sidebands is only 33% of the total power that we use to transmit our double sideband full carrier signal. So that means only 33% power are used to to carry information, to transmit information. All right. The other 67% is wasted in sending the carrier. Yeah. Okay, so that is for this slide. Any questions on this slide before I move on? No? No? Okay, I move on.
No question.
All right. So we have seen that from the previous equation, right? Even when we modulate the double sideband full carrier signal at its maximum value of modulation index, the sideband power, which is the useful power, is only 33% of the total transmitted power. Basically, this graph show you that. And of course, if you decrease the modulation index, this is on your x-axis here. If you decrease your modulation index, you can see that the power in sideband actually reduce significantly, while the power in the carrier occupying even more and more portion of the and of the total transmitted power. So you can see that as far as double sideband full carrier is concerned, even though it saved our problem at recovery where we don't require synchronous detection, it actually wastes a lot of power. All right. So here I actually rewrite the equation here. Yeah. And so we need to actually calculate the efficiency of this double sideband full carrier system. So the efficiency is defined as the percentage of the total power carried by the sideband. All right. So what it means is the efficiency, I'm going to use this symbol for efficiency, is the power in the upper sideband plus power in the lower sideband divided by the total power. All right. And what is total power? Total power is power in the upper sideband plus power in the lower sideband plus the carrier power. All right. So if we were to substitute the expression for this, all right, so basically, okay, let me put it in here. Power in the upper sideband and lower sideband. Okay, if I were to extract from this equation, all right, the power in the sideband basically is this one, m squared over 2. M squared over 2 PC. All right, whereas the total power is 1 plus m squared over 2 PC. All right. So now if you cancel PC and then you rearrange the terms, then you're going to get the efficiency basically is 2m squared over 2 plus m squared. And we normally express efficiency in percentage, then you multiply by 100%, then you get your efficiency. Okay. Right. So that's how we arrive at this equation. Yeah. So again, efficiency is what is M? M is modulation index. I hope we know it by now. So we can see that to increase the efficiency, we can actually increase the modulation index, but we know our limitation. The maximum value of the modulation index is 1. Okay, never use M more than 1. And with this maximum value of M equals to 1 will give you a best efficiency of 33% only, all right, which is what we have derived from just putting M into this equation. Then you get your 30% or 33% efficiency. Okay, so never use M more than 1 because that will result with your AM signal being distorted and not able to recover. Yeah, your original message can never recover at the receiver. So let's look at one example here. Okay, this example, easy one. We have a 300 watt carrier modulated to a depth of 60%. Okay, depth of 60% meaning your M is equal to 0.6. All right, carrier power 300, it means your PC is 300 watt. So determine the total power in the modulated wave. So straight away you can make use of the equation that we have just learned. PC 1 plus m squared over 2, right? And that will be 300 1 plus 0.6 squared over 2. All right, and then that will give you let me see now. Okay.
35.4.
35.4.
35.4.
354, right? Cannot be 35.4. This is 300 times 1 will be 300 already. Okay, then. That will be 354 watts.
Okay.
Yeah?
Correct.
So that's the total power in the modulated wave. And what is the efficiency? All right, efficiency, you can straight away make use of the equation, all right, which is m squared over 2 plus m squared multiplied by 100%. All right, so in this case with 0.6 square plus 2 plus 0.6 square multiplied by 100%, and that will give you I think it's 15.25%. Right, very low efficiency, 15% only. Even 33 also is considered quite low, 1/3. Yeah. So that is the problem with the double sideband suppressed carrier. Double sideband full carrier signal. All right, efficiency is rather low. Okay. Okay, looking at this answer and this expression, can you tell me how much power we have in the sideband? How much power do we have in the sideband? Just an extension of the discussion here. How much power do we have in the sideband?
27, Miss.
27?
Volt.
Yeah, okay. So how you get 27?
M square divided 4 times power carrier.
Yeah, okay, good. So basically, the power in the sidebands, you can straight away take the m squared divided by 2 times 300, and the total is actually 54 watt. But if you were to split it, then the power in the lower sideband equals to the power in the upper sideband. That is 27, yeah, 27 watt. All right. So you can see out of a total of 354 watt power used, yeah, only 54 watt is used to send the information. And out of this 54 watt, actually the information are duplicated. All right. Actually 27 watt is used to send the information. Yeah. A total of 54 watt if you actually consider both side bands. Okay, so all right, have you got this now?
Yes.
Okay, so I'm going to move on. Okay, in this example, you're asked to determine the power efficiency of the AM wave when modulation index is 0.5, 0.3, and then you need to compare your answer in A and B, right? And then suggest how the power efficiency can be maximized. Okay, so again, these questions, well, just make use of your equation, isn't it? Right, so again, efficiency is equals to m squared over 2 plus m squared multiplied by 100%. So just put in your 0.5 here, 2 plus 0.5 square multiplied by 100%, and that will give you I think 11.1%. All right, and then let's for B when it's 0.3. Then you have 0.3 square plus 2 plus 0.3 square multiply with 100%, and that will give you 4.3%. Okay. All right. So as far as calculation is concerned, if you actually come across any question that require calculation, and if you are using any equation to calculate, please write down the equation first. Because in case your final answer is wrong, at least you still got marks for your equation. All right. But if you don't bother to put down the equation, you straight away start with the putting in the numbers and then get the final answer. And then what happens if you put in the number wrong, which is quite common because sometimes you don't put a 1 here instead of 2. All right. And then sometimes you don't press wrongly on the calculator, end up the final answer is wrong. If that is wrong, then you got 0 marks. But at least when you have your equation written down, you still got 1 mark for your equation. Okay, so all right, so let's compare. Let's compare the answer we get in A and B. So in A, when the modulation index is 0.5, yeah, we have an efficiency of 11.1%. And then when the modulation index is reduced to 0.3, our efficiency has also been reduced to only 4.3%. So what can you say? So what can you say? Can you say about the efficiency? Or relate it to modulation index, because you got your efficiency from modulation index, isn't it? Okay, so 11.1, 4.3. So talk about overall. Okay, so overall efficiency is low, right? Overall efficiency is low. Yeah. And how to relate the efficiency to modulation index? Okay. Huh? The efficiency decreases when the modulation index decreases. All right. So the efficiency actually reduces or decreases when the modulation index decreases. So it decreases along in together lah, yeah. So you are expected to be able to make this kind of conclusion, okay, or deduction based on the your result of your calculation. Right. So get used to it, because you are now in year 3. So I expect you to do all this. If you are not able to, then make sure you pick up. Okay, D, how could the power efficiency be maximized? How do we maximize our power efficiency here?
Increase the modulation index to 1.
Yes. Good. Can be maximized by setting modulation index to 1. All right. Okay, this is the exact answer I'm looking for. The power efficiency can be maximized by setting modulation index to 1. In the past, whenever I ask this question in the exam, not many students can get it right, I was very, very surprised. Because they always say the power efficiency can be maximized by increasing the modulation index. Increasing modulation index is not the right answer. All right, because I'm asking for maximizing. Maximizing means the best. All right, so to get the best, there can only be one value. So don't tell me increasing power by increasing modulation index. No, I cannot give you mark by saying increasing modulation index. Because modulation index, you can increase to any value. What is the value that give you the best result? Yeah. So you have to say modulation index must be set to 1 or increase to 1. Okay, I'm looking for this value 1, 1, 1. Yeah. So this is okay, this is the answer for part D in example 5. So I hope you learn as well as I explain all this in lecture, okay, and in the example, and as well as in the tutorial questions. So don't ask me for hint at the end of the semester. I give you hint along as I discuss it, all right? Because I don't remember all my hint later on. Okay, so shall I move on?
Yes, you may.
Yes.
move on.
Yes.
Okay, right, let's recall the two drawback. Okay, the first drawback we already addressed it, which is the power efficiency. All right, you can see that more than 67% of the power is lost in the carrier. Okay, more than, because minimum is 67%. Yeah, why minimum is 67%? Because the maximum efficiency is 33%. All right, so it can be lower, depend on your modulation index. And let's address the second bandwidth. Bandwidth, we double sideband full carrier signal use as far as bandwidth is concerned, it use 2 times the necessary bandwidth, because we actually transmit 2 sideband that contain the same information. All right. So in order to improve its performance, all right, we can actually address these 2 drawbacks. Yeah. The first one is, okay, carrier is the one that make me waste more power. So I don't send the carrier. Okay, that means I'm going to suppress the carrier. By suppressing the carrier, that brings us back to double sideband suppressed carrier, isn't it? All right. Okay. And then are actually carrying the same information. So I just send 1 sideband. I don't want to send 2 sideband. So I address the second problem. Okay. So the new modulation scheme, or the modified modulation scheme that can address these 2 problems is called single sideband suppressed carrier. All right. We suppress the carrier now, and we only send 1 sideband. So this is single sideband suppressed carrier modulation technique. Yeah. So which sideband shall we send? Either one. You choose whichever sideband you like to send. All right. The lower sideband or the upper sideband. So in the single sideband suppressed carrier signal, then 100% of the power is used to carry the sideband. Yeah. And because there's no carrier, that's all. So you actually make 100% use of the power. Yeah. And single sideband suppressed carrier signal only need half the bandwidth. Yeah, only need half the bandwidth because you only transmit 1 sideband. Okay, the question is, how do we generate this kind of signal? Okay, the generation of a single sideband suppressed carrier signal actually is very similar to double sideband suppressed carrier signal. Same thing, we multiply. Okay, we multiply the incoming, the message signal with the carrier signal. All right, that will give us a double sideband suppressed carrier signal here. Then what we do next is to use a sideband filter. All right, sideband filter, which allow only 1 sideband to pass. All right, and after that, the filter output will actually give you only the single sideband that you can use to transmit. Yeah. So again, as far as the spectrum is concerned, let's say this is the message, the spectrum of the message signal or the modulating signal. All right, and then the double sideband signal spectrum, we're going to have 2 sideband, right? So this is your lower sideband, this is your upper sideband. Okay, so take for example, what I have here? Here we are actually, I want to send my lower sideband. So what I use is, I use a lower sideband filter. That will give me my lower sideband that I can transmit. But if you want to send the upper sideband, then you design a bandpass filter. Okay, in this kind of process, you definitely need a bandpass filter. All right, your sideband filter basically has to be a bandpass filter. All right, so your bandpass filter, again, if you center at the here, then that will allow you to center frequency is this one, and then the pass band of your bandpass filter has to be the bandwidth equivalent to the bandwidth of the baseband signal, then you're able to pass the upper sideband signal. All right, upper sideband signal, and then you only transmit the upper sideband. Okay, concept-wise is very easy, but how to actually realize it is not that straightforward. Okay, all right, so there are three ways to generate the single sideband suppressed carrier signal. The first one is the selective filtering method, the one that I've just explained previously. Okay, what is the problem with selective filtering? Yeah, if you look at the double sideband signal being generated, all right, how well can you design your bandpass filter? Yeah, how well can you design a bandpass filter? Because what I was talking just now is I assume my filter is ideal, right? My filter is ideal, so I can actually filter the band that I want perfectly out, so I can transmit things as it is. This is when you can design a filter that perform ideally. Yeah, but in practice, you know that ideal filter does not exist, right? You can actually increase your for filter design, how do you increase your cutoff here so that it's as sharp as possible? How do you improve this? Make sure you have sharp cutoff here in your filter design. By increasing your filter order, isn't it? Yeah. Hello, you return everything to your lecturer already. So if you increase your n, the order of filter, yeah, you can actually improve this transition here instead of something like that. Yeah, because your in practice the filter window, right, depend on your n, right, on your order of filter. So if you use let's say your n, which is low, right, you won't be able to get this lower sideband out perfectly, because you're going to get something like here again, right, and then you're going to get something like that. Yeah, that's for if you use a filter of a very low order. But if you increase the order, yeah, of course you can improve a bit. Yeah, you can improve a bit. So instead of this noise or this unwanted signal that that manage to escape through your filter, you can actually reduce its amount by increasing your n. All right, but by increasing your n, there are consequences, isn't it? Yeah. What are the consequences? No answer. Okay, you go and figure out it. I don't want to talk about filter. This is not filter course. Okay. All right. So the selective filtering method, basically, want to say is not easy to achieve in practice. All right. So let's come to the second method, which is a phase shifter method. All right. So in the phase shifter method, okay, this is a bit more complicated. So what we do is we are going to make use of two double sideband suppressed carrier modulator. Basically, it's just multiplier, the double sideband suppressed carrier modulator. So what I'm going to do is I'm going to make use of two double sideband suppressed carrier modulator, as I mentioned, and I'm also make use of two phase shifter. All right, two phase shifter. And then the function of this two phase shifter is to shift the phase of my message signal as well as the carrier signal by 90 degree, pi over 2. All right. So now my message come in here. All right, my message come in here. Okay. So this message will be used to modulate. Okay, I'm going to multiply. Double sideband suppressed carrier modulator, basically just a multiplier. All right, multiply with what? Multiply with the carrier signal here. Okay, this is a carrier signal, cosine wave. Then I'm going to take, at the same time, I'm going to take the message signal. I'm going to perform a phase shifting process so that I can get the other version of my message signal. That version is this, the original one being phase shifted by 90 degree. All right, and I'm going to multiply it with, again, the same shifted version of my carrier signal. I also shift my carrier signal by 90 degree. So I multiply these two. Message shift by 90 degree, carrier shift by 90 degree, then I multiply them. All right, and I get the another product out here. Okay, I have another product out here. So that I have two signal coming up. So one is the original version of the message multiplied with the original version of my carrier signal. On the other branch here, I have the product of the phase shifted version of the message and the phase shifted version of the carrier signal. So what I do next is I either add them or subtract them. All right, I either add this to this or I subtract this from this, depending on which sideband I want to transmit. All right, depending on which sideband I want to transmit. So to illustrate that, let me put in an expression for my MT so that it makes more sense to you. All right. So let's say my MT is equals to, again, I'm just for simplicity's sake, I'm going to use cos omega MT. All right. So the phase shifted version, I shift a cosine by 90 degree. What I get here is a sine. All right. Same thing here. I shift my cosine signal or for my carrier. I shift my carrier signal of a cosine omega CT by 90 degree. I get a sine. All right. So what I have here is sine omega MT multiply with sine omega CT. Okay, so what I have here is cos omega MT cos omega CT. Right? Now, make use of our trigo identity again. Right? So this one again will be cos X cos Y. Yeah. So what I have here will be equals to half of cosine omega C minus omega MT plus cosine of omega C plus omega MT. Right? And then for sine, what do I get? Sine A, sine B, or sine X, sine Y will give me half of cosine omega C. Let me get this right first. Sine of omega C minus omega MT minus, is it correct? Yeah, someone check the appendix and let me know because I forgot to refer to my appendix before this. Cosine of omega C plus omega MT. Okay. Okay, if I plus, so if I plus, what do I get? If I plus, what do I get? Okay, now, so if I want to add, so if I add the signal coming up from the on the upper path here, all right, with the signal that come from the lower path here, I add this to this, all right, I add this to this, so I'm going to cancel this term. I'm going to cancel this term with this term because this is plus, this is minus. All right. So what I'm going to get is, if I plus, then what I'm going to get is, I'm going to get cosine omega C minus omega MT. All right. So here, what I'm sending is, I'm going to send my lower sideband. Yeah. But if I minus, if I plus, if I plus and plus, this is what I get. But if I were to minus, All right. If I were to take that plus and I were to minus this one, then this is plus, this is minus. So I'm going to minus. So this term will be gone, right? And this term minus minus become plus. So what I'm going to have is I'm going to get omega C plus omega MT. So here, what I get is I get my upper sideband. Yeah. So that depends. So depend on which sideband we want to send. So we do the necessary operation here. So that's for phase shifter method. Yeah.
Can.
And let's move on to the third method. All right. Okay. Before we move on to the third method, let's talk about the second method first. What's the weakness of the second method? Okay. The main weakness of the second method is in the phase shifter. All right. Again, in practice, it's not easy to get a phase shifter that give you exactly 90-degree phase shift. All right. It could be some drift, could be some tolerance. So if we do not get the exact 90-degree, then our theory here will not work already. Okay. So again, the signal that the result of the signal that you get after the phase shifting will not be what you expect. Yeah. So this phase shifter method, even though theoretically it does work, practically it's very difficult to implement. And that brings us to the third method, which is called Weaver method. So this I think is developed by a gentleman surname Weaver. That's why it's called Weaver method. So Weaver actually suggested that we do a two-stage SSB modulation. All right, two-stage SSB modulation. Let's go back to actually his problem. His method is to address the problem with the selective filtering. Okay, you see, the selective filtering, we're going to have problem designing our filter. All right, especially when our upper sideband and our lower sideband are so close to each other. So how do we do a sharp cut off? Yeah, you want an upper sideband, you want lower sideband. It's very difficult to do a sharp cut off, especially when you have what do you call that? Significant amount of power at low frequency. So if your spectrum has significant power at low frequency, so basically it's very difficult. Practically it's very difficult to actually split your upper sideband from your lower sideband. All right. So what Weaver suggests to improve the situation is to actually perform a two-stage single sideband modulation. So what he suggests is in the first stage, all right, we modulate the baseband carrier with a baseband signal with a low frequency carrier. All right. Because for AM modulation, the carrier frequency is at about 500 plus kilohertz, isn't it? 500 plus kilohertz to 1006 kilohertz. So he suggests do not modulate straight away with the carrier of this frequency. Use a low frequency first. All right, use a low frequency first, and then we filter the sideband there after the first modulation. We filter the sideband out after the first stage modulation, right? Then after that, we treat the single sideband that we have filtered out as a new baseband signal, and now only we modulate with the high frequency carrier. Okay, so that is Weaver's method. And why we do it in two stages instead of one stage, right? Again, one stage we know we have problem designing the filter. So the benefit come from filtering is much easier at low frequency as compared to high frequency. All right, you learn your filter design before, right? Yeah, you learn your filter design. So let's take a filter, a simple filter. Let's say first order filter. All right, first order filter, what is the attenuation like? Attenuation first order minus 3 dB per octave or minus 20 dB per decade, right? There's attenuation in it. Attenuation meaning reduce the amplitude of the frequency component by so much, right? So if you actually design your filter for low cutoff frequency, let's say I use a cutoff frequency of let's say my cutoff frequency is let's say 50K, 50 kilohertz. All right, 50 kilohertz. Then that means at minus 3 at my cutoff frequency, all right, I have minus 3 dB attenuation. All right, and at 2 times my cutoff frequency, I actually have 2 times that would be per octave. So I have another 3 dB. So I have 6 dB attenuation. And at per octave, meaning what? 10 times, right? 10 times my cutoff frequency, I'm going to have minus 20 dB, what do you call that? Attenuation. So minus 20 dB, minus 20 dB is actually equals to 1 over 100. So meaning at 10 times or cutoff frequency, which is 500 kilohertz, all right, the effect, all right, the frequency component at that frequency will be reduced by 100 times. Okay, so meaning I can do a good filtering here when it's 10 times. But if I were to use a higher carrier frequency, let's say 500K, I straight away modulate to 500K for my AM signal. So I only achieve the same attenuation, all right, at what? 5 megahertz, you know. All right, 10 times of 500K will give me 5,000K. So at 5,000K only, I can achieve, what do you call that, attenuation of 100 times. But if I were to, the same filter, but if I were to use a lower frequency, at let's say 50K, right, at 500K, I can already achieve 100 times attenuation. Okay, that's the concept behind it. So again, you do not expect what do you call that, 100% attenuation. So, but the lower the effect, the lower the component, the effect of the frequency component at the frequency that we don't want, then better the attenuation is, right? So basically, the effect of attenuation is to reduce, right? Reduce the component, the frequency component of the signal that we do not want, right? So that is the idea behind Weaver method. Okay, still not the best, but at least a bit better than the selective filtering method. Okay. Oh, almost three already.
Okay.
Almost three already. So let me see. Okay, recovery. Do you have a class after this?
Yes.
Yes. At 3 o'clock.
Yeah.
Okay. Then I better release you, or else your children may not like it. Yeah, but good thing about the online classes is 1 second you are in my class, the next second you can be in another class already, isn't it? Save the walking of 5 minutes, 10 minutes, or 15 minutes. All right, so let's stop here for you go through it yourself. If you have any question, then we can always discuss again during our next lecture. All right. Okay, I'm going to stop sharing. If you have any questions, then you can always stay back a bit. I'll wait, and then I'll wait in case you have questions.
Thank you, Miss.
Yeah, bye-bye.
Thank you, Miss.
Yep, thank you.
Thank you, Miss.
Thank you.